So we're very happy to have our last discussion of this week, of this focus week. We'll still have a seminar, and this will be on resurgence in exact quantization, and it will be led by Gergő, who will have a few people speak about this. So please, Gergő.
Okay, thank you very much, Ines. So in this session, we will have two talks. The first is given by David Suzanne from IMCCE. He will talk about resurgent properties of WKB solutions or Schrödinger equations with polynomial potentials, a historical overview, and he will also talk about his ongoing research project with Frédéric Fauvet and Riccardo Schiappa. And after that, we will have a discussion on his talk, which will be followed by a talk by myself on Borel summability and problems related to singularities on the Borel plane, connection formulas, and so on. So now I would like to ask David to start his talk.
Sorry, just 1 second. André, can you switch off your microphone? Can you mute yourself for the time being?
Yes, yes, absolutely.
Thank you.
Okay. So I'm not able to share my screen. Could you make that possible? Maybe you can make me co-host or something like that.
Done?
Yeah, that works. So where is my presentation? Here. So thank you very much. I'm very happy to be virtually in Cambridge, Isaac Newton Institute. So, and thank you for giving me this opportunity to speak on Borel summability and resurgence. And as mentioned by Gergő, it's a historical angle I would like to take. So here is the first page. I hope you can read clearly. Good. So let me talk about the early history of quantum resurgence. So this phrase was coined, I suppose, by Jean Écale. So what is the history? We have here with us André Voros, and you know his famous paper published 1983 about the return of the quartic oscillator. Maybe you are slightly less familiar with his Bourbaki seminar delivered in late 1982, in which there was this story of analytic bootstrap in the context of exact WKB method. And there was the relation with Écale's theory of resurgence. And here there is a story to tell. André will correct me if necessary, but what I understood is that André had written a nice preprint, and he had been to Grenoble to talk with famous French mathematicians, Bernard Malgrange and Yves Collin de Verdière, and he was showing his results about Borel summability, moving the ray of integration in the Laplace transform. That's the very important thing. And this phenomenon of analytic bootstrap, many things were conjectural, but there were numerical evidence, many calculations. And immediately Bernard Malgrange told André, you should talk to Jean Écale. He has a theory about that kind of phenomenon. So that was around 1980, 81 maybe. And this is how André Voros for the first time heard about resurgence and Écale. And so indeed, he went to talk to Ekal, and Ekal was, I suppose, enthusiastic to see this beautiful application of his theory, and vice versa. Certainly, André was interested in having a theory corresponding to what he had been doing. And this is why in '84, Jean Ekal, in this very important preprint about irregular singularities and multiple resurgence, mentions quantum resurgence, mentions the WKB method as an example in which his resurgent theory can play a role. So you notice here, I'm really focusing on the French part of the history, omitting all relevant contributions. Previous to that, there were contributions by Shibuya, Balian Bloch, etc. And but well, on the French side, and starting with that point, with that interaction, let's say, between Voros and Ekal, then we have the Nice school. I mean, Frédéric Pham, who was professor in Nice, and his PhD students, Delabarre and Dillinger. And their thesis was defended in '91 with that title. And as you can see, contribution to quantum resurgence, Voros resurgence, and Yost function. So, and then there was this famous paper, DDP, published '93, Delabarre, Dillinger, Pham, published in Annales de l'Institut Fourier, Grenoble, Voros resurgence and periods of hyperelliptic curves. So let me skip all the further contributions by the Nice school, by the Japanese school. Well, let me just mention this revival of the interest for resurgence in that context, maybe triggered somehow by this preprint by Gayotto, Moore, Knightsky in 2008, and also in other directions by Kontsevich, Zeubelman. There were interesting things. Okay, today I would like to walk you through these two papers, the Ekal '84 preprint and Delabarre Dillinger PhD thesis, because there is an appendix. I mean, the first part of the thesis is yes.
Structure en académique, c'est quoi?
Non, c'est plutôt des, comment ça s'appelle, des...
I think somebody has not muted himself. So I was saying the PhD thesis has a first part which gave rise to essentially that paper up to changes. But there is an appendix in the thesis which has not been reproduced in the paper 93. And this appendix is interesting for the present discussion, because here the question is how far we could go rigorously, mathematically, in proving various statements about Borel summability and resurgence. So far, we can say that the proof of resurgence, let's say the statement by Ekal, the proof has not been provided fully. However, for Borel summability, we can find very interesting things already in those papers, at least in this framework. So here is an excerpt from Ekal '84. You see it, I'm sorry, it's written in French, but you recognize the stationary Schrödinger equation. So here X is maybe 2 over h bar, and W is energy minus potential, or maybe potential minus energy, I'm not sure. So Q is the configuration space variable, you know, like in classical mechanics, Hamiltonian mechanics, you have Q and in the configuration space, and P would be the conjugate momentum. And in this context, P is essentially square root of W. So this change of variable, Z, is very important. Z is the new variable instead of Q. And you see, this is the change variable which straightens this vector field, 1 over square root of q d over dq. And so z is an action integral, but if you view it as a new coordinate, it's a coordinate in which certain differential operators will become with constant coefficients. So here you recognize the WKB solution. So C plus C minus are arbitrary constants. Remember, X is H bar. So you put whatever constant, not depending on Q, that is on Z. The exponentials of the problem are exponential plus or minus exponential, so plus or minus xz over 2. You have the usual term dq over dz square root, so which is w power minus 1/4. And then you have the series proper normalized here. The normalization is that phi plus and phi minus are series with constant term 1. And when I say series, I mean they are in non-positive powers, in integer powers of the large variable. X is a large variable, large complex variable, in fact. So this is the corresponding equation for phi plus and phi minus. And you observe that here we have a constant coefficient for this differential operator. And here we have a function, very important. So it's h squared minus h prime, where h is this half the second derivative of q divided by q first derivative of q in the variable z. So this function h will play a role because its singularities will be responsible for the singularities of the Borel transform of phi plus and phi minus with respect to x, because this is what we want to do, to analyze the Borel transform of phi plus or minus with respect to x. So I hope it is clear so far. And you see here, this is in the middle of this very long paper. So in this very long paper by Ekal about multiple resurgence, irregular singularities, Schrödinger equation appears as an example. So it's the second example. And for that case, Ekal coins the term quantum resurgence. Now we go on with another page. So this is later in the same paper. So, well, in this example, we were focusing on the polynomial potential, for which more is known than for a more general case. But apparently, in the end of the article, Ekal returns to that Schrödinger equation, envisioning a much more general W. So still the same notations. And you see that if QW is polynomial, then there is equational resurgence, which corresponds to Shibuya's work in the 70s. And what is more important is that more generally, so this will be the case, what's next is the case when W is polynomial, but not only in this case, the function H that we have seen. So the function H, you remember, in fact, it's a rational function of Q deduced from W expressed in the variable Z, and Z is a ramified variable. So H of Z in the polynomial case, you see at infinity, it has this nice 1 over Z decay, but even at infinity, it has a Puiseux expansion, as you can see here. And then when you come from infinity, you encounter singularities in the Z plane with a ramification. Again, typically you have a cubic root branching or things like that, and poles also. And Ekal says, well, what you need for the theory to work is that this function H be endlessly continuable, that is prolongeable sans coupure, endlessly continuable, that nice analytic continuation, possibly with multi-valuedness, and this will give rise to quantum resurgence. That is a claim by Ekal. And here you see this interesting paragraph. Polynomial potentials, especially the quartic one, have been studied by Voros, the return of the quartic oscillator. Voros has conjectured resurgence with respect to X and at most exponential growth of the Borel transforms, which, as you know, will allow us to take a Laplace transform. So this at most exponential growth is essentially Borel summability. And here, this conjecture is true. The demonstration, the proof will rely on that change of variable we have mentioned already, Z as a function of Q, and on the following remark. And here is the remark. So it's an expression for the Borel transform of phi plus. So you remember the notations. Phi plus is the series part in the WKB expansion when you choose plus in the exponential. Of course, what you get for phi minus will be very analogous. So phi plus is what we are interested in. And here is a claim, the Borel transform of phi plus with respect to X. So we keep variable Z, X, the large parameter, 1 over h bar has been replaced by Xi. You get Dirac at the origin. This is because the series was starting with constant term 1, and Dirac is the image of 1 by Borel. And then you have a series of holomorphic functions of Xi, holomorphic for Xi close to the origin, provided Z is moving not anywhere. Typically, Z moves, well, it's written here, close to Z0, some auxiliary point, which is not a singular point for H. And this function H, you see, it appears everywhere. So let's have a closer look at the formula. So the claim is that there is a series representation for phi plus hat, the Borel transform, a series of Wn hat, and you distinguish odd and even, but it's always multiple integral, very explicit. You see a larger and larger number of variables, of integration variables. And this integrand is just a product of H evaluated at these points. And the integral is over I to n or I to n plus 1. This is an integration multipath because you have so many variables. And here is a very precise description of the multipath. So these expressions, so let me translate for you the last sentence. These expressions are valid for Z close to this auxiliary point Z0 and for Xi close to the origin. They are easy to bound, easy to analytically continue with respect to Z as well as with respect to Xi. And for the proof which had been announced, that's all. I mean, in that 84 paper, Ekal says nothing more about the proof for WKB. He said, okay, you go to variable Z and you obtain this representation of the Borel transform of the WKB expansion. Now, let's have a look at Delabarre-Dillinger PhD thesis directed by Frédéric Pham. And you see that in the jury, we find again Malgrange, Ekal, Voros, and Nosmas. You know his name maybe through the book by Pham, Nosmas, and Kandelberger. So what the title is Contribution to Quantum Resurgence. And let me draw your attention to the appendix, because this appendix of the thesis has never been published. I talked recently to Eric Delabarre via email, and he confirmed me that for working on his thesis, he communicated with Ekal, and Ekal kindly sent him material, drafts, and he helped him to recover these integral representations, and he guided him and he helped him to get the bounds. So Delabarre-Dillinger didn't get everything of Ekal's result, of Ekal's claim, but well, let's see what part they obtained. So Here, there is a slight change of notation. The wave function is capital phi. So phi plus, now the plus is on the left, you see. Phi plus and phi minus, they are as before. And the plus is on the left because he wants to decompose it as phi minus plus phi plus. So let's focus on the plus in the exponential. So we have phi minus plus phi plus, and minus and plus, this will be for even and odd. You remember in Ecal, the multipath of integration, blah, 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 it was, you had to distinguish odd and even indices. And in fact, it is possible to obtain this system, I mean, this decomposition of phi in the sum of two unknowns, which satisfy a system of ODEs. And then when you go to the Borel plane, you will get a system of PDE. So you are interested in phi minus and phi plus simultaneously because their sum is what you need. And okay, here is the way you obtain the integral representation. It's not written here, but these iterated integrals will be nothing but the Neumann series for solving this problem. You see, we have a linear ODE, a system of ODEs. So there is a method here, very natural, to solve it by induction, which is the Neumann series. And what it produces is exactly this. You see, you need to invert repeatedly this operator, dz plus constant. And the constant is either 1 or 0, sorry, either x or 0. You see dz here, dz plus x here. Well, it's convenient to enlarge the framework because here you need dz minus x. So what they do, they say, okay, whenever eta is a sequence, a finite sequence, you call absolute value of eta the sum of the values. In fact, these are complex numbers and this absolute value is not positive. Typically, there will be plus x or minus x or empty set. Well, empty set, it's easy. And then you construct inductively on the length of the sequence, you construct a family of series. So this is at a formal level in X. So the claim is that when eta is a sequence of plus or minus X, then this defines inductively W eta, a formal series in X. In fact, it's not totally defined because determined because sometimes, I mean, if the sum of the elements is 0, then you are free to choose the integration constant. And this was the rule of the auxiliary point Z0. And so this is how you get the representation as a sum of various objects. You have cut the problem into smaller pieces. And now what are these pieces? Well, when you go to the Borel plane, you get PDEs and the image, the Borel image of W with the sequence reduced to a plus, here it is, minus h to z in z minus xi. If the sequence is like this, then you get this, etc. So you recover these iterated integrals exactly the same as in Ecal. So here you understand the origin, and now they tell you in their appendix what you can do with that. Well, maybe I don't want to speak too much, too long, so I will skip that part. You need to analyze the analytic continuation with respect to xi of these functions, because now you see that the Borel transform clearly are holomorphic functions of xi. And second, you want to bound them in order to prove at least Borel summability. So what they did is that, well, this is an analogy with something in Borel, very old paper about convolution. Let me skip that. The idea is that when you have a function defined by an integral, so typically, well, this is the convolution integral from 0 to xi, and xi moves. And f and g have singular points. So if xi moves along a ray, avoiding singular points, that's okay, because xi1 and xi minus xi1 will avoid the singular points. But as soon as xi meanders between the singularities, it's a different story. You have to deform your integration path. And it will be the same here, I mean, this is a simple integral, this is a double integral. You have to deform the path of integration or the multipath in order to obtain analytic continuation. But this is not always possible. Well, this will be very often possible because, well, you have a lot of flexibility thanks to Cauchy theorem or Poincaré-Cauchy theorem for the multiple integration case. But of course, you have to be careful that at the end of the path, this you cannot act on the end, you cannot deform it. I mean, in between you can deform, but at the end, if you hit a singular point, then you are in trouble. So this is why singularities appear in the Borel plane, in the psi variable, and these singularities produced by the endpoints of the path of integration or in the multipath in general. Where did they happen? Well, believe me, you can follow their argumentation. They have happened when psi reaches pi minus z0. Z0 was just the auxiliary point. By the way, very often you can put it at infinity, and it's probably more clever. But then pi is a singularity of this h function. So you remember the function h, a combination of the potential evaluated in variable z. So in fact, the singular points of pi, the singular points pi, they are what we could call the classical periods in this context. At least the differences of these pi's are periods of some algebraic function here. Now, if psi plus z0 is pi, or if psi z minus psi is pi, then you have singularity. So you see, and this is more interesting, actually, the second case. So the second end of the path, this one gives you a moving singular point, moving because z is certainly a variable. So when z moves, the singular point moves. So this is due to the end. You cannot act on the end. Now, we said we can deform a lot our multipath, but, well, sometimes you have a pinching singularity. When you move, you deform your path, but you have something to avoid, so you deform like this, and you have something to avoid like that. And then when they collide, you are in trouble. And this gives rise to singularities at the differences pi prime minus pi of singular points of h. This is how they obtain this statement, which is proved, that one in the appendix. So it's a statement about the holomorphic star. You see on étoile, the holomorphic star, the Mittag-Leffler star of the function. So the idea is that Z has moved from your initial point to Z0, it has moved somewhere, and then where you have arrived, you take psi. It was initially very close to the origin, but you want to send it to infinity in order to compute the Laplace transform. Is it possible? It's possible provided your ray avoid fixed singularities of that kind, pi minus Z0, moving singularities Z minus pi, or fixed singularities pi prime minus pi. And they claim they have at most exponential growth at infinity and for the function, and they obtain that from bounds for the Borel transform of the elementary blocks. You remember these iterated integrals, you distinguish odd and even case, you distinguish the case when Z0 is at finite distance or when Z0 is at infinity. Well, in all cases, they claim when provided you go along rays in the psi plane, they claim that they can obtain these estimates. And if you get that, you see that indeed the sum of these elementary blocks will be a uniformly convergent series of holomorphic functions in appropriate sets. And this will prove the final result as far as the Mittag-Leffler star is concerned. They humbly recognize that they don't know how to do the other sheets of the Riemann surface. But you see that they have, in fact, there are pages and pages of computations of bounds to reach that. And they did not publish it because they considered, well, that was too little. I mean, they were more interested in the analytic continuation in the further sheets. And this, they could not do it. And so they did something else with FAM, taking for granted Ekal's claim. I'm sorry I spoke too long. I thank you for your attention.
Thank you very much, David. Thank you for this informative talk. So now we are open for discussion.
Yes, may I make a comment?
Yeah, please.
Yes, David, you describe very beautiful historical papers, but I wonder why and it happens quite often, that you're neglecting the contributions of Dingle, because in the 1970s, in his book, which actually refers to work he did in the 50s and in the 60s, which I heard you speak about, he explicitly understands, certainly for the WKB case, this resurgence of the high coefficients and the low being related, and he actually implements this as a summation procedure, which we later extended and called it hyperasymptotics, but he did it, and he calculated explicitly for a number of special functions of analysis using this resurgence, the summation beyond the smallest term in the WKB series. And that's an explicit application, and he envisages continuing the process. He uses the phrase, and so on, stage after stage. And he clearly recognizes that you can interpret, he uses this expression very much, the WKB series as something exact, using Borel's summation. And he couldn't go further. And I'll tell you why, because he did all his computations on an old hand calculating machine. And there was one machine that enabled him to get the various coefficients you need to 30 digits. And that was enough for what he couldn't go any further, because you needed, and you get these enormous coefficients, as you know. But so he clearly envisaged the procedure. He didn't use the word resurgence. And Ekal, in his paper, explicitly refers to Dingle's resurgence formula for the coefficients. So I'm slightly disappointed that although now we go much further, and certainly Ekal and Boros did, but why this pioneering work of Dingle is rarely referred to. So can you explain this?
Oh, yes. I'm sorry if I gave the impression that I'm neglecting Dingle's work.
Yeah.
It's not my intention at all to underestimate his contribution. I was focusing on admittedly a tiny part of the story, because I wanted to show some detail, maybe technical details, but I wanted to show how detailed was the analysis by Ekal and Delabarre-Klinger. But I agree. I mean, Dingle is explicitly referred to by Ekal and also by Boros, by the way.
Yes, yes.
So I mean, Dingle was absolutely not ignored, neither by André Boros nor by Ekal. My choice, I mean, it's absolutely subjective, was to, in a small amount of time, and even then I spoke too long, to show the technicalities of Ekal's approach, because our feeling with Schiappa and Fauve is that this could be pursued to finally obtain the proof of that claim, because that claim by Ekal in 84, the claim about the resurgence has never been proved in detail. Ekal was announcing various papers, and he did not provide that. He wrote many things, but something else. And rather late 90s, Frédéric Pham I would say, publicly confessed that he didn't know how Ekal would do the full proof of his theorem. As I tried to convince you that Pham and his students, and I mean, Delabarre particularly has continued the collaboration with Pham, they mastered the details of the analytic continuation at the level of the pieces, and also at the level of Borel summability, but something was lacking. You see, it's a combination of analysis, you want bounds to prove that something is uniformly convergent, complex analysis because you need to deform the path to prove that the analytic continuation exists, and combinatorics. I didn't mention that word, but in fact, do you still see my screen? Oh, yes. I should have said that this expansion here, is it here? I don't know. Yes, this is a mold expansion in Ekal's terminology. Mold. And apparently, Ekal's strategy was to use his mold theory, which is a kind of combinatoric apparatus, to study fully this family of elementary resurgent functions. So my feeling is that it was worth telling that story, but I fully acknowledge that this is only a part of the history. And I don't know how Dingle would have proceeded in order to reach the conclusion for the whole Borel transform of phi plus or phi minus. I ignore that. But I wanted to show that something could be done along these lines, and we hope with Chiappa and Fauvet to pursue that. But it's a bit complicated, I must say.
Yes, I agree exactly, and it was, I completely understand. I just want to say something in the opposite direction, because my understanding of what Dingle had done, even though I was his student in the 1960s, was not until really 1988. And actually, it was while I was working in Nice, I spent a month, and from Frederick Pham, I learned about these new developments. And it was for the first time I started looking at the high orders. And it was because of the conversations with him that I was able to understand this microscopic structure near a Stokes line. It was while I was in Nice, and they had an old unused up in the attic Hewlett-Packard computer, desktop computer, which I was able to use, program it in BASIC to actually do the numerical checks of this Stokes smoothing. I heard about it already in 1988. So it's understood. I don't want to. There's no sense of competition, and certainly no sense of nationalism. Dingle would have really enjoyed these developments. Unfortunately, he was sick for most of his life. There were long periods of time when he couldn't concentrate and he didn't go into the department. He suffered from various chronic and painful illnesses. But okay, the point is made, and we understand each other. And André, certainly, I know, is fully aware of this prehistory. So thank you for clarifying that.
And thank you for adding these very interesting historical aspects. Most of them.
May I add a comment? My microphone is very bad, so I'm cutting it, but I made a remark on chat.
Oh, let me find it. Yes, agreed. Good. Perfect. Thank you. Very good.
Oh, yes, of course. Yes, the announcement paper by André, I should have quoted it. It's prior to his Bourbaki seminar. It's a note des comptes rendus de l'Académie des Sciences. And indeed, I have it and I confirm. But well, by lack of time, I chose to not to.
And actually, if you allow me a little joke, I could say something else. I mean, I first learned about André's papers, these massive contributions, in the 1970s and his early papers. And these were enormous. And in Bristol, we referred to this work as the Vorosaurus.
The Vorosaurus.
Vorosaurus. But this was certainly intended respectfully. I'm sure Andre will appreciate that. Okay.
Yeah, I discovered now Andre's chat.
Yes.
Thank you, Andre, for the confirmation and for the added information. It's certainly very relevant. I think this story needs to be told. I mean, not only the French side, of course. I mean, but here everybody is, I think, appreciative of Dingel's contribution. Mm-hmm.
Okay, I have one question. So, is your strategy to prove the resurgence along the lines presented in the appendix of the thesis?
I would say yes. Yes, we already have clues. I mean, a method that we call the vector field method to produce the deformation. You know, I show a brief picture inspired by Borel. It's for the case of a simple integration. You integrate on the contour between 2 points, and it's the same if one of the points is at infinity, and you get a function which is, let's say, a function of the endpoint, and you want to check where you can follow its analytic continuation. Well, with a contour integration, maybe you can draw pictures and convince yourself of what happens. The question was, what about the multi-dimensional case? You have iterated integrals, and what about the bounds? I mean, even with a simple integral, the deformation may be very complicated and very meandering everywhere in the complex plane. So you need to control at least the length. The minimum you need for analysis is to control the length of your deformation with respect to the initial length. So that's one thing. And what about the multidimensional case? So we have a machinery based on auxiliary vector fields whose flow, the time one map, let's say, of the vector field is, or let's say not the time one, but the time t map. The flow at time t is a family indexed by t of homeomorphisms. I mean, the flow of a vector field is a homeomorphism, and it's a continuous family of homomorphisms that we want to use to deform the initial path. So the idea is to construct the vector field so that its flow will be a suitable deformation. And now we are speaking of a vector field. If you have a formula, maybe you can use, what's the name? I mean, estimates for the flow of a vector field. Gromval estimates, I mean, something rather basic to control the deformation when you know well enough the vector field and the initial path. And if, of course, if the initial path is very long, okay, the new path will be long, but you want to control all that. So we have a method to do that. And on the mold calculus, we have already a bit of expertise, but it's work in progress. And let me just say it's not finished.
Okay, thank you. So Andre has
another comment by Voros. If you want to read, Gergő.
Yes, I was about to do that. So Andre wrote, I've seen remarks that ECA was to finish the proof in the fourth volume, never published. However, I noted somewhere the following substitute reference. David, can you please comment on it, as I don't have it with me? Thanks. Les fonctions Resurgent.
Oh, volume 4. Yeah, I mean, Les fonctions Resurgent, this is the famous series of books, volume 1, 2, and 3. 81, 81, 85, and then they are thicker every time. And volume 4 was never published. It's always announced in preparation. As far as I I think Ekal wants to write it, but I mean, I'm not in his mind. And so, in fact, I don't know. I don't know if or whether Ekal one day will publish something on that subject. I'm afraid he's already fascinated by so many topics, new topics in the last 20 years. I mean, multi-zetas and many other things. Also, the multi-zeta work by Ekal is entirely built on mold calculus. In fact, a variant of mold calculus, which is called the bimold calculus. So I don't know if we will see. I mean, I know nothing about a preprint for volume 4. That's my answer.
David, pardon, tu peux regarder ce que j'ai rajouté dans mon chat?
So you mean Ekal was to finish the proof in a 4th volume never published. However, I noted somewhere the following substitute.
C'est peut-être Ekal lui-même qui m'avait parlé de cette référence. But perhaps Ekal, I don't remember, but he said that to look at this paper.
Ah, you mean the paper published in Costin et al. Volume, Analyzable Functions?
Yes.
Should be this. Oh, no, I know that paper, and I know for sure that it does not contain the proof.
Okay.
I know that paper, and it's I should check. I know that paper, but I don't quite remember the content. But I mean, if it contained a proof, the proof that we are waiting for, I would remember it. That's for sure.
Are you sorry? You?
I would remember if it contained.
Okay, good. Thank you. Thank you very much. I will tell Malgrange, because every time I see him, he asks me what's going on.
Maybe I could recall what I said in a previous discussion, that there is some recent paper which is on title Scrambling Operators applied to multi-zeta algebra and singular perturbation analysis, which is the most recent contribution of Ekal on this subject. But it's sure that it's still quite far from an analytic proof such as David would like to see, and there are more than the contribution to new object whose study could be a step towards this proof.
I agree with you. I agree. This most recent paper is full of interesting combinatorics, but it does not contain any detailed proof for WKB. Well, still, it maintains that in principle, it should be applicable to WKB. Maybe it's mentioned somewhere, but nothing more.
Okay, let me proceed to the second talk if there are no more questions or comments. So let me share my screen. Can you see it?
Yes.
Yes.
Okay, thank you. Yes, so I'm going to talk about Borel summability of WKB solutions for quite general one-dimensional Schrödinger equations, and problems on singularity structure and connection formulas. So the equation I'm going to consider is of this form. So second derivative equals u squared fuz and then the function. So u will be the large parameter, which can be real or complex. And z is the independent variable, which lies in some domain D, bounded or otherwise, of a Riemann surface. And we have the potential function f that can depend on the large parameter u as well. And we assume that it is an analytic function of z on D, and then it possesses a Borel-summable asymptotic expansion of this form. So it can be expressed for large U as a Borel-summable divergent series of this form. And it is further assumed that these coefficients here are all analytic functions of Z in the domain D, and they are independent of U. And initially, I will suppose that the leading coefficient F0 does not vanish in D. So similarly to what was described by David, we will make a change of variables given by the Liouville transform. So I introduce the new variable, which I denote by psi. So I'm more or less following the notation of Frank-Over throughout the talk. So this is different from Ekal's notation or the notation used by the Japanese school. So it just, okay, sorry, I'm missing a subscript 0 here. So we take the square root of the leading coefficient and then integrate it from a fixed point z0 up to z. And then I introduce a new unknown capital W, which is a function of u and psi in this way. Again, this is f0. And I assume that the path of integration, except perhaps its endpoint z0 is lying entirely within the domain D. And if z0 is a boundary point, then I assume that the integral converges as t tends to z0 along the contour of integration. And with this transformation, we transform the domain D into some domain G. And then in terms of these new variables, the original equation becomes of this form. So we eliminate the factor of u square. And then we have something I denote by phi. This is the multiplier of the linear term in u. And it can be expressed in terms of f1 and f0 in this form. And then we have a psi, which also depends on u, and it can be expressed in this form in terms of the original fuz and the first two coefficients in its asymptotic expansion. And these are holomorphic functions of psi in the domain G. Now the Borel-summable series of the potential f is transformed into a Borel-summable series of psi itself, and it has this form, and you can express all the coefficients in terms of the coefficients of the original series. And these are again holomorphic in G. And then the most convenient way to write the WKB solutions to this transformed equation is of this form. So you can check by substitution that the equation has two solutions of this form, where the coefficients an plus minus can be computed by a recurrence relation that I'm not going to reproduce here. And those are analytic functions of psi in G. And we are interested in the Borel summability of this series. So let me define two domains. B of R denotes the open disk in the t-plane with radius r, and UR denotes all the points whose distance to the positive real axis is strictly less than r. So here's a picture. So this is BR, circle with radius r, and then this whole white domain is the domain UR. For the Borel summability, we have to make some assumptions on the coefficient functions of the differential equation, the transformed equation. Initially, I would like to normalize the solutions at infinity. So I'm making almost the most general conditions under which this is possible. So I assume that the function phi multiplying the linear term in U, this one, is bound. So there is a domain, a subdomain of G, which I denote by delta, which has the property that there are two positive constants C and rho, which are independent of U and Xi, such that these bounds hold. So these functions, phi, its derivative, and the leading term of the divergent expansion of the function psi are bounded, and they have to tend to 0 at infinity with certain rates. So these two have to tend to infinity, 0 faster than the reciprocal. There is a more relaxed condition for phi here. And then we have to assume the Borel summability of the divergent expansion of psi u psi. For that, I have the following condition. So that there is a function, capital psi, t psi, which is analytic on a domain. So in the t variable, it has to be analytic in a domain u to d prime. So this u is the neighborhood of the positive axis, where this prime is some positive number, and it is analytic in the domain delta specified here. This d prime has to be independent of u and psi, and this function has the following properties. So it grows at most exponentially in t, in this domain u to d prime, and it decays with respect to psi at infinity with this rate, similarly to these two functions. And that this is the Borel transform of the divergent expansion of psi, that is psi u of psi equals psi 0 psi plus the Laplace transform with respect to u of this function. And this holds for sufficiently large values of u and for arc psi in the domain delta. I will need a further notation to specify the domain of analyticity of the WKB solutions with respect to the independent variable. So I introduce for each solution a domain denoted by gamma. So let D be a positive number. And let me denote by gamma plus minus D any known empty subdomains of the domain delta specified in the previous slide that satisfy the following two requirements. So the distance between each point of these domains and each boundary point of the domain delta has a lower bound D, which is to be chosen independently of U. And if psi is in gamma plus minus, then any translate of psi is also in the domain. For example, for gamma plus, if psi is in gamma plus, then if you subtract any positive number from psi, then that point has to be in gamma plus as well. I will show a picture of a typical domain gamma minus in a moment. Note that this condition requires delta to contain at least one infinite strip that is parallel to the real axis, and in particular delta, and hence G has to be unbounded. And so we seek solutions of the exact solutions of the differential equation of the following form. So the leading order exponential, and we replace the divergent WKB expansion by exact function, which I denote by eta plus minus function of u and psi, where the real part of u will be larger than some constant sigma, and psi will be in these domains specified here. And as I said, I would like to normalize the solutions at infinity. So I require that eta plus tends to 0 as the real part of psi tends to minus infinity. And similarly, eta minus tends to 0 as the real part of psi tends to plus infinity. So here is a typical domain gamma minus. So these functions can have singularities in the domain G, so at psi1, psi2, psi3. So we delete a certain neighbor. So if we make cuts in the negative direction from these points and delete the neighborhood of these cuts, and you can see that if you have a point in the unshaded region, which is gamma minus, then if you add to it any positive number, then you still remain in the domain. And so this is the result on the Borel summability. So let D be a positive number, which is less than D prime specified in the conditions. Let sigma be a sufficiently large positive number. If the condition for the coefficient function of the equation hold, then the differential equation has two solutions of the form given above, where these eta functions are analytic functions with respect to u in a half plane of this form, and analytic functions of psi in these domains gamma plus minus d. And these functions satisfy the limit condition specified here, so this limit condition. And moreover, it can be represented as a Laplace transform of some function, capital F plus minus. And this capital F plus minus is the Borel transform of the WKB solutions. And it has the following properties. It is analytic with respect to t in a 2D neighborhood of the positive axis, so in U2D, and analytic function of psi in gamma plus minus d. It has this usual expansion in the neighborhood of the origin, which is a convergent series. And we also have an estimate for the Borel transform. So for each r which is less than d, there is a positive number k plus minus, or there are positive numbers that depend on this sigma here and on this r, and are independent of t and psi, such that this estimate holds. So the Borel transform goes at most exponentially. Sorry. And in the respective directions, it tends to 0, so that eta satisfy the limit requirement at infinity. And I said here that sigma is sufficiently large, so this integral will converge for sufficiently large values of the real part of u. The current result I have is this. So you can take sigma to be any number that is bigger than 3/2, sigma prime plus 1. Sigma prime was the exponential bound for the capital psi function, or 38 times c. C was the, so this is this c, and this is sigma prime. But I wonder if one can lower this bound further. Certainly you cannot go below sigma prime. So just quickly, few words about the proof. I will say more in a specific case. So the main idea is to construct a function which satisfies the corresponding Riccati equation, and I denote this function by h plus minus. And so we write this 1 plus eta plus minus as the exponential of a Laplace transform of an integral function. And the first step is to construct this function in the neighborhood of the origin. This can be done by algebraic type estimates for the coefficients A of the WKB solutions. And then we extend this function to the neighborhood U to D of the positive axis using partial differential equations. And let me comment on the conditions for this Borel summability result. So in fact, you can relax the conditions on the potential functions, these functions that I gave a few slides before. So they need not to tend to 0. It is enough to assume that these functions are just bounded on some domain delta. And the Borel summability will still hold, except that you cannot normalize your WKB solution at infinity. But you can normalize it at any finite point in the domain delta, so that eta plus minus is 0 at some specified points, psi plus minus. Okay, so we constructed the Borel transforms in a neighborhood U2D of the positive axis, but we still don't have any information about the singularities in the Borel plane. So we just explore the small neighborhood of the plane. And we do not know what happens near the Stokes lines either, or Stokes curves in the original variable Z. I would like now to comment briefly on the singularities and then outline a strategy on how to obtain the connection formulas, and also information about the type of singularities in the case of a simple turning point. So for simplicity, I'm going to consider a very special case of the equation. So it is of this form. There is a function multiplying the large parameter u square. And that is a f1 is missing, the multiplier of u, and then the remaining part is independent of u. If you apply the Liouville transform, you end up with this equation. So this is actually the equation that was usually studied by Frank Olver as well. And so the WKB solutions may be written in this form, as I explained. So using this solution of the corresponding Riccati equation. And then if you plug this into the equation and focusing only on the subdominant solution, so which means that we consider H minus, then you find that H minus satisfies this integral equation here. So this is a convolution, and I assume that convolution for now is taken along a straight path on the plane. And so the idea is to solve this integral equation. And to do that, we specify first the domain, which I denote by capital omega. So this contains pairs of complex numbers t and xi. Yes, I have to say that we assume that we already constructed a solution near the origin. So we'd like to extend it into a strip around the positive axis in the right half plane. So I just assume that t has positive real part and the imaginary part is at most 2D. And there is a condition between the two variables that xi plus r over 2t must lie in delta for all r between 0 and 1. And you can check that the domain claimed in the theorem U2D product gamma minus d is contained in this omega. Now let sigma be an arbitrary fixed positive number, and let me denote by curly b sigma the complex vector space of analytic functions ht xi on this domain omega, such that for each h in this vector space there is a constant k that depends on sigma, such that this estimate holds. So these functions grow at most exponentially, they decay at infinity in a certain rate. And for technical reasons, I have to introduce this extra factor of 2 plus the absolute value square. And then we define a norm of all these vectors, the functions, to be the infimum of all such constant k for which this inequality holds. And then it turns out that with this norm, B sigma becomes a Banach space. And then if you equip it with the convolution as an operation, then B sigma is a Banach algebra. And then you can define an operator that acts on each h in this way. So you replace capital H by H. And then you show that this operator is a contraction on the unit ball of this space. And the fixed point will be the required solution, capital H minus. But as you can see, this constructs the Borel transform eventually just in a small neighborhood of the positive axis. So what about singularities? So again, H minus satisfies this equation. And if I denote by psi k labeled by positive integers, the singular points of psi 0, then we can observe that this side of the equation actually makes sense for any psi in G and for any t that lies in the plane with branch cuts emanating from these specific points. So these points depend on psi. So here is a picture of it. So if you translate psi with such t, then you never encounter any of the singularities of this psi 0. So this equation makes sense. And I believe these are basically the movable singularities that were also discussed by David. So this is the guess. And it seemed to work for the general equation. When you have more general potentials, you have to take into account singularities of the function phi and the capital psi function as well. But it seems that the singularities will always have this form for the subdominant solution, and similarly for the other solution as well. But I couldn't use this information to actually extend the analyticity of the Borel transform because you see the admissible domain for the t variable depends on the other variables. So in that sense, that is not a function because the domain in the first variable is not fixed. So I cannot define a suitable Banach space where we could solve this integral equation. Perhaps it can be done by complexifying the large parameter at the beginning and absorbing the phase of the large parameter into the potential function and solve this problem for each fixed phase of the large parameter, and then get Borel transforms in certain strips that will avoid these singularities. And then perhaps returning to the original variable, we can glue together all these different Borel transforms into a single one and see that for each fixed psi, the Borel transform is indeed singular at these points only. So here I just would like to give two concrete examples to support this claim. So the first one is I believe the simplest is the ARA equation. So if you perform the Liouville transformation for the ARA equation, then the corresponding psi 0 is just a simple rational function of this form. And it is well known that the Borel transform can be written in terms of the Gauss hypergeometric function. And so the only singularity of this function is the origin. So psi 0 is 0. And we can take G to be the plane taken away the origin. And then, knowing the analytic properties of the Gauss function, we can see that the Borel transform is singular exactly at this point minus 2 psi plus 2 psi 0, which is just minus 2 psi. So then this becomes 1. A less trivial example is provided by the Legendre equation. So if you take a certain version of the Legendre equation where the large parameter is the order of the Legendre functions, then after Liouville transformation, you end up with this potential function. So it's the reciprocal of the square of the hyperbolic sign. And fortunately, we can compute the Borel transform here for the subdominant solution, again, in terms of Gauss hypergeometric function, but with more complicated argument. And so the singularities of this function are at integer multiples of pi times I. And you can remove these from the complex plane to get your domain G. And then from the properties of the Gauss hypergeometric function, we can see that the singularities of the Borel transform are indeed at t equals minus 2 psi plus 2 psi k, that is at minus 2 psi plus 2 pi I k for any integer k. Okay, to finish the talk, I would like to comment on the connection formula problem. So I consider the same problem as at the beginning, except that I would like to focus on a simple turning point. So I suppose that the leading coefficient F0 vanishes exactly at 1 point in our domain D. So now it can vanish, which I denote by Z0. This is supposed to be a simple 0. That is a simple turning point of the equation. And then we make a slightly different change of variables this time. So from Z to zeta, given by this formula, and we introduce a new unknown function, this curly calligraphic W, and then the equation becomes of this form. So now the large parameter is multiplied by zeta, and then these coefficient functions are analytic in the image of D, in the zeta image, which I denote by H. And this transformation maps the simple turning point Z0 into the origin in H, and the three Stokes curves issuing from Z0 are mapped into these rays in the H domain. And then you can recover the previously discussed solutions, the simple capital W via these transformations from between psi and zeta. And so the works by Bill Boyd and Frank Over on turning point problems suggest that under suitable conditions on these functions, the potential functions, the set of all solutions of these transformed equations is of this form. Here, AI denotes any solution of Airy's equation. So we have any solution of Airy's equation with a certain argument involving this capital phi function and also the derivative of the same solution. And these are multiplied by certain functions of u and zeta. And we expect that for sufficiently large values of u, these coefficient functions A and B are holomorphic functions of theta in an appropriate subdomain of H that includes the turning point and also the Stokes rays. And as functions of U are described asymptotically by descending power series in U. Moreover, these asymptotic series are Borel summable. So since these functions are analytic in a neighborhood of the turning point, we can see that the continuation formulas across the Stokes rays will be described by those for the solutions of the ARA equation. And moreover, using the Borel transform of solution to ARA equation and the Borel summability of these objects here, together with the Borel summability of the coefficient functions, we can actually decompose the Borel transform into convolution and sum of Borel of some functions, and the singular part will be coming from the Borel transform of the solution of the ARA equation, and this will show us eventually should show us that for turning points the type of singularity will be of simple type in the sense of égal. And that's the end of my presentation. Yes, answer to Andre. I can give you something. I have a paper on a special case of this, what I discussed here. So I can share that with you. So if you have any questions or comments, then please feel free to ask.
Can I ask a question?
Yes.
Just like, so what could you hope to use to decrease the bounds of your theorem in terms of Borel summability? Is it, sorry, just another question. Is it just because it's a general case? If you looked at particular examples, is it possible that in particular examples you could decrease that bound?
Yes, thanks for asking. I wanted to actually say that. So I think I can decrease it to sigma prime when t is positive, so on the real axis. But as soon as I move away a bit, then I can't. Also, if the divergent series in the potential function is not there, just the leading term, which is independent of u, the psi 0, then I can show that sigma can be taken to be any positive number. I saw in one of the talks last week that they took the large parameter to be 1. So it might be useful to have a relatively small lower bound for the real part of u, so that you can use this theorem in those cases as well.
I have a question on the Legendre equation. So how is it in the Z variable? I mean, you gave the Legendre equation with a certain psi 0 of psi, so psi is the UV coordinate. Where does it come from, this psi 0? There is a parameter mu, I remember.
Yes, so there are actually two transformations. So first you transform it into an equation of the original form that I had in Z. And there are two parameters in the equation, the mu and the nu of the Legendre, usual Legendre functions, if you like. And the u, what I denoted by u will be nu plus a half. So I didn't write down here the transformation and I don't remember it exactly, but that's what you will have. So if you move first to the Z variable, then the u will be played by nu plus a half. And then you do the Liouville and then you get this hyperbolic sine function. And then to obtain the Borel transform, you can use the solution. One of the solutions will be basically the Q function, the Q Legendre function at nu times hyperbolic cosine of psi. And you basically use a integral representation of that function to recover this explicit form of the Borel transform. I don't know if it's possible for the speaker to ask a question from the audience. Someone might be able to answer, especially people from Japan. So I'm aware of work by Koike Shefke, and I would like to hear comments on how their work is related to what I described here. So if anyone who knows the details could comment on this, it would be very much appreciated. Okay, Andre has another comment. General remark, my empirical observations were that my Borel transforms with respect to 1 over h bar were actually much better behaved than necessary, bounded at infinity on each ray. Has anybody an idea on how to prove such a fact? Perhaps if you know the behavior of your solution and well enough in large domains, and then you represent the Borel transform as an inverse Laplace transform of the solution, then maybe you can use bounds on the solution to recover bounds on the Borel transform. But
maybe I can comment on Voro's question. André has a different normalization for the Borel transform itself. I suppose this is why he wrote my Borel transform. André systematically uses that the Borel transform is of, let's say, large variable power n is Borel variable power n divided by factorial n. No shift of the exponent. Usually we take Borel variable power n minus 1 divided by factorial n minus 1. Of course, there is a relation between the two transform, but it's an integral relation. I mean, André's Borel transform will be something like integral from 0 to psi or of our, something like that. So you have to be aware of that. to interpret his question. I see that André confirms that he's alluding to that specific normalization. Because so the fact that his Borel transform will be bounded at infinity along a ray, that is not necessarily true for the usual Borel transform. So you have to be careful.
So as for the comparison with Koike-Shefke's work, it seems that there are some differences in details, but basically in Koike-Shefke's work, they constructed a solution of the Borel transform of the Schrödinger equation by using some iteration method after using the UV transform. So in principle, the outline is the same as yours, I think. But anyway, I do not understand the details fully exactly. So perhaps some differences may exist, but anyway, the outline is the same on the same line, perhaps.
Okay, thank you. Yes, Andre has one more comment. Yeah, I cannot resolve it at the moment. Of course, in the specific examples I showed you, it's probably true because the Gauss function will either be of power growth or will even tend to zero at infinity. Okay, if there are no further comments, then I would like to ask Ines to stop recording.